Long before there were oceans, before there was light, there was only a cold, dark cloud, drifting in silence through the Milky Way. Welcome to the Sleepy Lab. Tonight, we will travel back 4.5 billion years to the very beginning of our solar system, from a quiet cloud of dust to the birth of worlds. If you haven't already, consider subscribing, one sleepy soul at a time. Now, let's begin. Picture the Milky Way, a vast spiral of stars turning slowly in the dark. And somewhere within it, about 4.6 billion years ago, there floated a cloud. Not a cloud of water or rain, but a cloud of gas and dust, cold and still and impossibly large, stretching across light years of empty space. It had no name, no shape. Really? Just a quiet gathering of matter, hanging in the dark between the stars. This cloud was made mostly of hydrogen, the simplest element there is, along with helium, the second simplest. Together, they made up nearly all of it. But threaded through that hydrogen and helium were tiny traces of something else, heavier elements: carbon, oxygen, silicon, iron, atoms that had been forged deep inside stars that had already lived and died long before. Those ancient stars had burned through their fuel, collapsed, and scattered their remains across the galaxy. And some of that scattered dust found its way into this cold, quiet cloud. So even before our story truly begins, it was already a story of inheritance, of matter passed down from one generation of stars to the next. For a long time, perhaps millions of years, the cloud simply drifted, doing nothing at all. But then, something happened nearby. A star, not far away in cosmic terms, reached the end of its life and exploded. A supernova, one of the most powerful events in the universe, sent a shock wave rippling outward through space. That wave, or perhaps a strong, stellar wind from a massive neighboring star, reached the edge of our quiet cloud and pressed inward, gently at first, then with growing force. And the cloud, which had been balanced between its own gravity pulling inward and its internal pressure pushing outward, began to tip. Gravity started to win. The collapse was slow at first, almost imperceptible. But as the cloud drew inward, something else began to happen. It started to spin. Not because anything was pushing it in a circle, but because of a principle called the conservation of angular momentum. Even the tiniest, most subtle rotation the cloud already had became faster and faster as the material pulled closer together. Think of it the way water spirals as it drains. The motion was always there. It simply became more noticeable as everything drew inward. And as the cloud spun faster, its shape began to change. What had once been a rough, shapeless mass slowly flattened, pressed outward by its own rotation, until it became a broad, thin disk, spinning around a dense, hot center. This disk is what astronomers call the solar nebula, a vast wheel of gas and dust, glowing faintly with the heat of its own compression, stretching out across billions of kilometers. At the very heart of this disk, where the material was thickest and the pressure was greatest, temperatures climbed higher and higher. Atoms were squeezed together with such force that something remarkable occurred. Hydrogen nuclei began to fuse, merging into helium and releasing energy in the process. And with that, the sun was born. A new star, small and fierce and bright, flickering to life at the center of the spinning cloud that made it. But the young sun was not the calm, steady star we know today. In its earliest days, it passed through a turbulent phase called the T-Tauri stage, a time of violent outbursts and powerful stellar winds. These winds swept outward from the sun like an invisible tide, pushing away loose gas from the inner regions of the disk, clearing the space around the newborn star. It was a brief but intense chapter, the sun finding its balance, settling into the long, quiet burn that would last for billions of years. Meanwhile, farther out in the disk, something quieter was happening. Tiny grains of dust, each one smaller than a grain of sand, were drifting through the nebula, bumping into one another in the gentlest of collisions. And instead of bouncing apart, they stuck. This process is called accretion, and it is almost unimaginably patient. Grain by grain, speck by speck, these tiny particles built upon one another. Dust became pebbles. Pebbles became boulders. Boulders became objects a kilometer across, then 10 kilometers, then 100. These growing bodies are called planetesimals, the first solid worlds, if you could call them that, rough and misshapen, tumbling slowly through the disk. And the planetesimals kept colliding, kept merging. Over millions of years, the largest ones swept up their neighbors, growing heavier with each encounter, pulling in more and more material with their increasing gravity. Slowly, gradually, they became protoplanets, the ancestors of the worlds we know today. But not every part of the disk was the same. Close to the sun, where the young star's heat was fierce, temperatures were far too high for ice or water to survive in solid form. Everything volatile simply evaporated. Only the most stubborn materials endured: rock and metal, silicates and iron, the bones of future worlds like Mercury, Venus, Earth, and Mars. But farther out, beyond a certain distance from the sun, the temperature dropped low enough for something else to happen. Water could freeze. Methane could freeze. Ammonia could freeze. This boundary, this invisible line in the disk where ice could finally survive, is called the frost line. It sat roughly where the asteroid belt is today, about 2.7 astronomical units from the sun, nearly 3 times the distance between the Earth and its star. Beyond that line, the disk was rich with ice, and that abundance of frozen material would change everything about what formed there. But that is a story for the next few minutes. For now, just rest here, in the warmth of a young sun, surrounded by a turning disk of dust and light. Everything is still becoming. Beyond the frost line, where ice could finally hold its shape, something began to grow. Out in the cold reaches of the young disk, far from the sun's heat, frozen grains of water and methane and ammonia mingled with the rock and dust that drifted everywhere. And because there was so much more solid material here, so much more for tiny particles to cling to, things grew faster. Much faster. This is where Jupiter began, not as the immense world we know today, but as a quiet core of ice and rock, slowly gathering mass in the dark, pulling in grain after grain, pebble after pebble, one gentle collision at a time. Because ice was so plentiful beyond the frost line, Jupiter's core had an advantage that no inner world could match. There was simply more to build with. More solid material meant more collisions. More collisions meant faster growth. And faster growth meant Jupiter's core reached a critical size before anything else in the solar system came close. About 10 times the mass of the Earth. That was the threshold. Once the core crossed that line, something changed. Its gravity became strong enough to do more than attract rock and ice. It began pulling in gas, enormous amounts of gas, hydrogen and helium from the surrounding nebula, drawn inward and downward in great spiraling currents. The core became a seed, and the gas became its atmosphere, layer upon layer upon layer, until what had been a modest ball of ice and stone was wrapped in a vast envelope of swirling cloud. Jupiter was becoming a giant, and it did so with a kind of quiet inevitability. Once the runaway began, there was no stopping it. Gas poured in from the disk for perhaps a few million years, and when it was done, Jupiter held more mass than all the other planets that would ever form, combined. Farther out, Saturn followed a similar path. Its core grew in the same way, ice and rock accreting in the cold disk, crossing that same critical threshold, pulling in gas from the nebula around it. But Saturn formed a little later than Jupiter, and by the time its core was ready to gather gas, there was less of it left. Jupiter had already claimed so much. So Saturn grew large, but not quite as large. A giant in its own right, wrapped in golden clouds, but forever in the shadow of its older, more massive neighbor. And then, even farther from the sun, in the thinnest, most sparse regions of the disk, two more worlds were taking shape: Uranus and Neptune. Here, the material was spread so thin that growth was painfully slow. Collisions were rare. The building blocks were scattered across vast distances, and so these two cores grew with a patience that bordered on stillness. By the time they reached a modest size, the gas of the nebula was already fading. The sun's early winds were pushing it away, and there simply was not enough left for Uranus and Neptune to capture the thick atmospheres their larger siblings wore. They ended up with only thin envelopes of hydrogen and helium wrapped around cores of ice and rock. Giants, yes, but a different kind. Ice giants, as they are sometimes called, cold and blue and quiet. And here is where the story takes a turn that no one expected. Because Uranus and Neptune may not have formed where we find them today, there is evidence, subtle but persuasive, that these two worlds originally took shape much closer to the Sun, perhaps in the region between where Saturn and Jupiter now orbit, and only later drifted outward to the distant orbits they hold now. The solar system, it seems, did not simply form and stay still. It rearranged itself. A model developed by scientists working in Nice, France, proposes that the giant planets once orbited in a more compact arrangement, closer together, closer to the Sun. And then, after hundreds of millions of years of relative calm, a gravitational interaction between them sent everything into motion. Orbits shifted. Neptune swept outward. Uranus followed, and the outer solar system was reshuffled like cards on a table. This is called the Nice model, and it explains many things that a simple, static picture of the solar system cannot. Jupiter, too, may have wandered. There is a hypothesis that early in the solar system's history, Jupiter migrated inward, drifting closer to the Sun, carving a path through the disk of gas and dust before Saturn's gravity tugged it back outward again. This journey inward and then outward is sometimes called the Grand Tack, like a sailboat turning against the wind. And if it happened, it left a mark. Because as Jupiter moved inward, its gravity would have scattered and starved the material in the inner disk, particularly in the region where Mars was trying to form. There simply was not enough left for Mars to grow as large as its neighbors. This may be why Mars is so small. Earth and Venus had enough material nearby to grow into substantial worlds, but Mars, caught in the wake of Jupiter's passage, was left with only a fraction of what it needed. A world that might have been as large as Earth ended up with only about a tenth of its mass. A small, rust-colored planet, shaped not just by what was there, but by what was taken away. These four inner worlds, Mercury, Venus, Earth, and Mars, are called the terrestrial planets, from the Latin word for Earth, because they are made mostly of rock and metal, the stubborn materials that survive the heat of the young sun. Each one is different, shaped by its own particular history. Mercury, the closest to the Sun, is a small, dense world with an iron core so large it makes up about 85% of the planet's radius, almost all core, with just a thin shell of rock around it, as if something long ago stripped away its outer layers and left only the heavy heart behind. Venus is nearly the same size as Earth, but it turns so slowly on its axis that a single Venusian day, one full rotation, takes longer than a Venusian year, longer than the time it takes Venus to travel all the way around the Sun, a day longer than a year, time moving at its own strange pace on a world wrapped in thick, hot clouds. Earth, our world. The third stone from the sun is, as far as we know, the only planet with stable liquid water on its surface today. Oceans that have persisted for billions of years. Water in motion, water at rest, water cycling endlessly between sea and sky. And Mars. Mars was not always the dry, cold desert it is now. Once, long ago, rivers carved channels across its surface. Lakes pooled in its craters. And there may have been a shallow ocean spread across its northern hemisphere, a body of water catching the light of a younger, kinder sun. That water is mostly gone now, lost to space or locked beneath the surface as ice. But the channels remain. The ancient shorelines remain, carved into the rock like memories the planet cannot quite let go of. 4 small worlds of rock and metal, each one born from the same disk, each one shaped by distance and chance and the slow pull of gravity. Rest with them for a moment. Mercury, baking in the sun's glare. Venus, turning in its own unhurried time. Earth, blue and breathing. Mars, holding the ghost of its rivers. They are all still here, still circling, still carrying the story of how they came to be. And so are you, drifting quietly in the warmth of this old, familiar star. Beyond Mars, past the ghost of its rivers and the silence of its red plains, there is a gap. A wide, quiet stretch of space where millions of rocky bodies drift in slow, patient orbits around the sun. This is the asteroid belt. It sounds crowded, and in a way it is. Millions of fragments of rock and metal tumbling gently through the dark. But if you gathered every one of them together, every pebble, every boulder, every mountain-sized shard, their combined mass would still be less than that of our moon. All of it, less than one small, familiar moon. They never became a world. They tried, in their way. Or rather, the physics of the early disk tried on their behalf. Dust gathered into stone, stone gathered into larger stone. But something held them back. Something enormous, pulling from just beyond. Jupiter. Even from a distance, Jupiter's gravity reached into that region of space and stirred it, tugging at the orbits of those early fragments, speeding some up, slowing others down, sending them crashing into each other, not to build, but to break apart. The material was there, but the hand of the largest planet would not allow it to settle, would not allow it to become whole. And so the asteroid belt remains a place of almost a world that never was. But within it, there is one body that came close. Ceres, a dwarf planet, round and quiet, drifting among the rubble, the largest object in the belt by far. Ceres is a modest world, small enough to fit within the borders of a single country on Earth. But beneath its dusty, cratered surface, there may be water, a layer of liquid or ice, hidden in the dark interior, kept just warm enough by the faint heat of its own small body. Even here, even in this scattered, broken place, water may persist. Let that settle for a moment. Now, let your attention drift outward, past the belt, past the last of those lonely fragments, toward the planet that shaped their fate. Jupiter, the largest world in our solar system, a planet so massive it contains more matter than all the other planets combined. A vast sphere of hydrogen and helium, wrapped in bands of cloud that move in slow, sweeping currents, storms that have raged for centuries. And around it, a family. At least 95 moons orbit Jupiter, 95 small worlds, each held in the gentle grip of that enormous gravity. Some are tiny, barely more than captured rocks, but 4 of them are large. 4 of them are worlds in their own right. These are the Galilean moons, named for the astronomer who first saw them through a small telescope in 1610. 4 points of light, moving night after night around the bright disk of Jupiter. The innermost is Io. Io is a world on fire, or rather, a world of fire, the most volcanically active body in the entire solar system. Its surface is covered in erupting vents and rivers of molten rock, sulfur in shades of yellow and orange and red, painting the landscape in colors that shift and change as new eruptions bury the old. Io is never still, never at rest. Jupiter's gravity and the pull of the other moons flex its interior like a hand squeezing a ball, and the heat from that constant flexing drives the volcanoes that remake its surface again and again. Next comes Europa. Europa is quieter on the surface, a shell of ice, cracked and lined with long, wandering ridges, pale and smooth. But beneath that ice, beneath perhaps 10 or 20 kilometers of frozen crust, there is an ocean. A global ocean of liquid water, more water, perhaps, than all the oceans of Earth combined, kept from freezing by the same tidal forces that torment Io. The ice flexes, the interior warms, and the water remains liquid, hidden, patient, circling Jupiter in the dark. Then Ganymede, the largest moon in the solar system, larger even than the planet Mercury, a world of ice and rock with its own faint magnetic field, ancient and cratered in some places, grooved and resurfaced in others, as though the moon tried, long ago, to remake itself, and then grew still. And finally, Callisto, the outermost of the four, and one of the most heavily cratered objects anywhere in the solar system. Its surface is a record of impacts stretching back billions of years, almost unchanged, almost untouched, a face that remembers everything. And yet, deep beneath that battered crust, Callisto, too, may hold an ocean, quiet water, far below, where nothing stirs. 4 moons, 4 worlds, each one different, each one carrying its own kind of stillness or its own kind of fire. Let them drift. Farther out now, farther from the sun, to the ringed world. Saturn. You have seen pictures of Saturn, perhaps that elegant shape, the pale golden sphere wrapped in bright, flat rings. But consider what those rings are. Countless particles of water ice, some no larger than a grain of sand, some the size of a pebble, some as large as a house, all orbiting together in a thin, luminous disk, each particle catching the distant sunlight and reflecting it back, together forming something that looks solid from far away but is really a river of ice, flowing in a circle that never ends. And those rings may be young. Saturn itself is ancient, 4.5 billion years old, born in the early days of the solar nebula. But the rings may be only about 100 million years old. They may have formed while dinosaurs still walked the Earth. A moon, perhaps, wandered too close and was torn apart by Saturn's gravity. Or a comet struck one of its icy satellites and scattered the debris into orbit. We are not entirely certain, but the rings we see today may not have been there for most of Saturn's long life. They are temporary, a passing ornament on an ancient world. Among Saturn's many moons, 2 deserve a quiet word. Titan, the largest, is a world wrapped in a thick atmosphere of nitrogen, so thick you cannot see the surface from above. Beneath those hazy orange clouds, there are lakes, not of water, but of liquid methane, cold beyond imagining, pooling in basins near the poles, a landscape that echoes Earth in shape, if not in substance. Rain falls on Titan, methane rain, drifting down through that heavy sky, gathering into streams, flowing into those still, dark lakes. And then there is Enceladus, small, bright, covered in fresh ice. Near its south pole, long cracks split the surface, and from those cracks, geysers erupt. Plumes of water vapor and tiny ice crystals, shooting upward into space, carried so high they feed one of Saturn's faint outer rings. Beneath the ice of Enceladus, there is warmth, there is liquid water, there is, perhaps, a small ocean with a floor of warm rock. Even here, even this far from the sun, water finds a way. Rest with that thought for a moment. Farther still, Uranus, a pale blue-green world, cold and remote, circling the sun at a distance where light takes more than 2 hours to arrive. Uranus is quiet now, but something happened to it long ago. Something struck it, something enormous. A body perhaps the size of Earth itself, slamming into the young planet with such force that it was knocked nearly on its side. Today, Uranus is tilted almost 98 degrees on its axis. It does not spin upright like most planets. It rolls, slowly, gently, like a ball turned on its side, making its way around the sun with its poles taking turns facing the light. No one saw it happen. No one was there to witness the collision. But the tilt remains, a scar written into the planet's very orientation, a memory held in the angle of its turning. And Uranus keeps that memory quietly, drifting in the outer dark, pale and cold and patient, saying nothing at all. Beyond Uranus, even farther from the warmth of the sun, Neptune waits. It is the last of the great planets. A deep, vivid blue, the color of a twilight ocean seen from very far away. Neptune is cold, unimaginably cold, and yet it is not still at all. Winds race across its surface at speeds that dwarf anything found elsewhere in the solar system. Over 2,000 kilometers per hour, faster than the speed of sound on Earth, faster than any hurricane, any cyclone, any storm our world has ever known. And no one is entirely sure why. Neptune receives so little heat from the sun, and yet something deep inside it drives these furious, howling gales, as though the planet carries its own restless energy, a quiet fury wrapped in blue. From a distance, you would never guess it. Neptune looks serene, a small blue jewel in the dark. But beneath that calm appearance, the atmosphere churns and races, endlessly, tirelessly, in the cold and the silence of the outer solar system. Neptune is not alone out there. It has moons, and the largest of them is called Triton, a strange and beautiful world, covered in nitrogen ice, with geysers that send plumes of dark material high above its frozen surface. But the strangest thing about Triton is the way it moves. It orbits Neptune in the wrong direction, opposite to the planet's own rotation, opposite to nearly every other large moon in the solar system. This tells us something. Triton was not born alongside Neptune. It came from somewhere else, drifting through the outer reaches of the solar system until Neptune's gravity reached out and caught it, pulled it in, and held it. Triton was captured, a wanderer that found an orbit and stayed. And now it circles Neptune backward, slowly, in the cold, a moon that was once free and is now gently, permanently held. Where did Triton come from? Most likely, from a place just beyond Neptune's orbit, a vast, quiet region called the Kuiper Belt. The Kuiper Belt is not a belt of rock. Like the asteroid belt closer to the sun, it is a broad ring of icy bodies, thousands upon thousands of them, stretching from about 30 astronomical units from the sun out to roughly 55, each one a frozen remnant of the early solar system. Small worlds of ice and dust that never gathered into anything larger, never became planets. They simply remained, cold and patient and unchanged, drifting in slow orbits at the edge of the sun's influence. And among them, one small world that was, for a time, called the ninth planet, Pluto. For decades, Pluto held that title, the farthest planet, the smallest planet, a tiny point of light at the edge of everything we knew. But as telescopes grew sharper and the Kuiper Belt revealed itself, it became clear that Pluto was not alone out there. It was one of many, one icy body among thousands. And in time, it was reclassified, not as a planet, but as a dwarf planet, a member of the Kuiper Belt, rather than a world apart from it. This does not make Pluto any less remarkable It has 5 known moons, and the largest, Charon, is so big relative to Pluto that the two do not orbit in the usual way. Pluto does not sit still while Charon circles around it. Instead, they orbit each other, turning around a shared center of gravity that lies in the space between them, like two dancers holding hands, spinning slowly together in the dark. Neither one leads, neither one follows. They simply turn together, far from the sun, far from everything. And beyond the Kuiper Belt, beyond even Pluto and its quiet dance with Charon, there is something else, something we have never seen directly, but believe must be there. The Oort cloud. It is theoretical, a shell of icy objects so distant that it stretches perhaps 2 light-years from the sun. 2 light-years. That is nearly halfway to the nearest star, a region so vast and so empty that the objects within it are separated by enormous distances, each one a tiny frozen body, barely touched by the sun's gravity, barely held at all, drifting in the outermost dark. We believe the Oort cloud exists because of comets, long-period comets, the ones that appear in our skies only once in thousands or millions of years, falling inward from every direction, not confined to the flat plane of the solar system, but arriving from above, from below, from angles that suggest a spherical source. Something out there disturbs them, a passing star, perhaps, or the slow, gentle pull of the galaxy itself. And one by one, over vast stretches of time, they are nudged from their distant orbits and begin the long fall toward the sun. Short-period comets, the ones that return more frequently, like Halley's Comet, with its familiar loop every 75 or 76 years. These likely come from closer in, from the Kuiper Belt region, where gravitational nudges from Neptune send icy bodies tumbling inward on shorter, more predictable paths. All of this, the planets, the moons, the comets, the Kuiper Belt, the distant Oort cloud, all of it exists within a bubble. The sun, even from this great distance, is still breathing outward, sending a constant stream of charged particles in every direction. The solar wind, it flows past Mercury, past Earth, past Jupiter and Neptune, and beyond, pushing outward, always outward. And as it travels, it inflates a vast invisible shell around the entire solar system. This shell is called the heliosphere, and everything within it is, in a sense, still touched by the sun. But the solar wind does not go on forever. At roughly 120 astronomical units from the sun, the wind grows thin, it slows, and finally, it meets the pressure of interstellar space, the gas and dust and radiation that fill the galaxy between the stars. This boundary, where the sun's influence ends and the space between stars begins, is called the heliopause. In 2012, a small spacecraft crossed that boundary. Voyager 1, launched decades earlier, still drifting outward, still sending faint signals home. It passed through the heliopause and became the first human-made object to enter interstellar space. Not with fanfare, not with speed, but quietly. A tiny machine, no larger than a small car, slipping from one kind of emptiness into another, carrying with it a golden record of sounds and images from a small blue world very far behind. Now, let your thoughts turn back from the edge of the solar system, back through the Kuiper Belt and past the giant planets, back to the inner worlds, to a time when those worlds were young. The early solar system was not the quiet, orderly place it is today. For hundreds of millions of years after the planets formed, the inner solar system endured a period of intense bombardment. Asteroids and comets, scattered by the shifting orbits of the giant planets, rained down on the young worlds, striking the moon, striking Mercury, Venus, Mars, striking Earth. The craters on the moon's surface, the ones you can see on any clear night, are scars from that time, a record of violence written in stone and shadow, preserved because the moon has no wind, no rain, no weather to wash the memory away. This bombardment was not only destructive, it may have been a gift as well. Many scientists believe that much of Earth's water, the water in every ocean, every river, every drop of rain, was delivered during this time, carried inward by comets and water-rich asteroids from the outer solar system, falling to Earth over millions of years, slowly filling the basins, slowly giving our world the one thing it needed most: water, arriving from the cold edges of the solar system to a warm, young planet that was ready to receive it. And yet, before the water came, before the bombardment scarred the young worlds, something even more dramatic had already happened to Earth, something that gave our planet its closest companion. Long before the oceans, long before the first rain, the Earth was struck by another world. Scientists call it Theia, a body roughly the size of Mars, hurtling through the inner solar system on a path that brought it directly into the young Earth. The collision was beyond anything we can easily picture. Two worlds meeting at tremendous speed, merging in fire and ruin, sending vast plumes of molten rock and vapor spiraling out into space. And from that ring of debris, slowly, quietly, the moon was born. This is called the giant impact hypothesis, and it remains the best explanation we have for how the moon came to be. One of the strongest pieces of evidence is something subtle, something you would never notice just by looking up at the night sky. When scientists studied the rocks brought back from the moon by the Apollo missions, they found that the isotopic composition of those rocks, the precise ratios of different forms of oxygen and other elements, matched Earth's rocks remarkably closely. Too closely to be a coincidence. The moon and the Earth are made of the same stuff because they were once, briefly, the same body, torn apart and reassembled into two. After Theia struck, the Earth was unrecognizable. Its entire surface had become a magma ocean, a sea of molten rock, glowing white and orange, stretching from horizon to horizon, with no solid ground anywhere, no continents, no crust, just liquid stone radiating heat into the darkness of space. It took millions of years for that ocean of rock to cool, for a thin skin of solid crust to form on the surface, cracking and sinking and reforming again and again, slowly, patiently, the way all great things take shape. And as the surface cooled, gases escaped from the molten interior, rising through cracks and volcanic vents, building the Earth's first atmosphere. Not the air we breathe today, not yet. This early atmosphere was composed mostly of volcanic gases, carbon dioxide, nitrogen, water vapor, thick and heavy, and nothing like the sky you fell asleep beneath tonight. But it was a beginning. And within that atmosphere, something remarkable was already happening. The oldest known minerals on Earth are tiny crystals called zircons, found in the ancient rock of Western Australia, dated to about 4.4 billion years ago, nearly as old as the Earth itself. And these crystals hold a secret. Their chemistry suggests that liquid water may have already existed on Earth's surface when they formed. Liquid water on a world that had been a magma ocean only 100 million years or so before. It is a quiet kind of astonishing that our planet cooled enough, settled enough, calmed enough to hold water on its face so early in its life, as though it were in a hurry to become the world it was meant to be. Let that settle for a moment. The moon overhead, born from a collision that shattered the young Earth, the oceans below, gathering on a surface that had once been molten stone, and all of it, every grain of rock, every drop of water, every wisp of atmosphere, held in place by the gravity of a single, ordinary star. The sun. It is easy to forget, lying here in the dark, how completely the sun dominates the solar system, not just in brightness, not just in warmth, but in sheer mass. The sun contains about 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust drifting between the worlds, all of it together makes up only about 0.14%. The solar system is, in a very real sense, the sun with a thin scattering of debris caught in its gravity. And even among that small remainder, the distribution is uneven. Jupiter alone contains more mass than all the other planets combined. roughly 318 times the mass of Earth. Saturn is large. Yes, Uranus and Neptune are substantial, but Jupiter dwarfs them all, a giant among giants, holding court in the outer solar system with its dozens of moons and its ancient, swirling storms. And all of it, the sun, the planets, the moons, the comets, the dust, all of it is moving. Not just the planets around the sun, but the entire solar system itself, drifting through the Milky Way galaxy at about 230 kilometers per second. That sounds fast, and it is. But the galaxy is so vast that even at that speed, it takes the solar system roughly 225 to 250 million years to complete a single orbit around the galactic center. One galactic year, longer than the age of the dinosaurs, longer than the time it took for complex life to appear on Earth. In all the time our planet has existed, the solar system has made this journey only about 20 times. And as it travels, the solar system does not move in perfect alignment with the galaxy around it. The flat plane in which the planets orbit, that ancient remnant of the spinning disk from which they formed, is tilted about 60 degrees relative to the plane of the Milky Way. Like a coin spinning at an angle as it rolls across a table, our little family of worlds cuts through the galaxy on a slant, drifting quietly through the stars. But within the solar system itself, there is a beautiful orderliness. Most of the planets orbit the Sun in nearly the same flat plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, all tracing their paths through a thin, shared disk of space. This is not a coincidence. It is a memory, a direct echo of the solar nebula, that broad, spinning disk of gas and dust from which everything formed. The planets were born in that disk, and they never left it, still circling in the same plane, in the same direction, after 4.6 billion years, like grooves worn into an old path. The solar system remembers its own beginning in the tilt of its planets, in the direction of their orbits, in the flat, quiet plane they all share. It carries the shape of the cloud that made it, the way a river carries the shape of the valley it carved long ago. And here, on one small world within that plane, the crust has cooled, the oceans have gathered, the atmosphere has settled into something almost gentle, and beneath a sky full of stars that are also moving, also orbiting, also remembering their own beginnings, you're resting, and all of them. Every planet, every moon swept along in its orbit, moves in the same direction the sun itself rotates. They all turn together, like a slow, silent wheel. This is the signature of that ancient cloud, the spin it carried as it collapsed, passed down, unchanged, across billions of years, from formless dust to the worlds we know. It is a quiet inheritance. And there are other inheritances, too, older even than the planets, older than the sun itself. Sometimes, a rock falls from the sky, a meteorite tumbling through the atmosphere, landing softly in a field or a desert. And when scientists look closely at certain meteorites, they find something remarkable. Tiny mineral crystals, smaller than a grain of sand, that did not form here. They formed before the solar system existed. These are called presolar grains. They were forged in the atmospheres of ancient, dying stars, stars that burned and swelled and shed their outer layers billions of years before our sun was even a possibility. Those tiny crystals drifted through interstellar space, became part of the cold molecular cloud, and survived everything that followed: the collapse, the heat, the spinning, the building of worlds. And they are still here, embedded in stone, waiting to be found. There is a kind of meteorite called a chondrite, and it is among the most primitive objects we have ever held. Chondrites preserve material that has remained nearly unchanged since the solar nebula. They are not melted, not reformed. They are, in a sense, frozen memories of the very beginning. Small pieces of the original disk, still carrying its chemistry, its texture, its dust. Within some of these meteorites, scientists have found something even more specific. Small, pale structures called calcium-aluminum-rich inclusions. These are the oldest known solid objects in the entire solar system, dated to about 4.567 billion years ago. They're the first things that condensed from the hot gas near the young sun, the first solid matter to exist in this part of space. Before the planets, before the moon, before the Earth's oceans or mountains or sky, there were these tiny, pale inclusions, quietly becoming real in the warmth of a newborn star. And so, the building began. Dust became pebbles. Pebbles became boulders. Boulders became the kilometer-wide bodies we call planetesimals. And inside some of those early bodies, something was happening. Radioactive isotopes, like aluminum-26, were decaying. And as they decayed, they released heat, enough heat to melt rock. The interiors of these young planetesimals grew soft, grew liquid. And when rock melts, it separates. The heavier metals, mostly iron and nickel, sank slowly toward the center, while the lighter silicate rock floated upward toward the surface. This process is called differentiation, and it gave the rocky worlds their layered structure, a dense metallic core wrapped in a mantle of lighter stone. It is the reason Earth has the interior it has today. Deep beneath your feet, far below the oceans and the crust, there is a core of iron, spinning slowly, immensely hot. And that iron core does something extraordinary. It generates a magnetic field, a vast, invisible shield that wraps around the entire planet, deflecting the charged particles streaming outward from the sun. Without that field, the solar wind would slowly strip away the atmosphere, molecule by molecule, until the air grew thin and the water began to disappear. This is not a hypothetical fear. It is what happened elsewhere. Venus, our nearest neighbor, lacks a global magnetic field, and over billions of years, the solar wind has done its work. Venus may have once had water, perhaps even oceans, but without that magnetic protection, the water was lost, broken apart by sunlight, swept away into space, leaving behind the thick, scorching atmosphere we see today. Mars tells a similar story, perhaps even more quietly. Mars once had a global magnetic field, but it faded early in the planet's history. And once it was gone, the atmosphere was left exposed, vulnerable to the steady erosion of the solar wind. Over hundreds of millions of years, the air thinned, the surface pressure dropped, and the rivers and lakes that may have once existed slowly vanished. Two worlds, two losses, both for the want of an invisible shield. Earth was luckier, or perhaps just the right size, with just enough heat in its core to keep the iron moving, to keep the field alive. Farther out, the gas giants have magnetic fields of their own, but generated in a very different way. Deep inside Jupiter and Saturn, the pressure is so immense that hydrogen itself is crushed into a metallic state, a strange, dense fluid that conducts electricity. And it is this metallic hydrogen, churning in the planet's interior, that creates their magnetic fields. Jupiter's field is staggering in its reach, roughly 20,000 times stronger than Earth's. It creates intense radiation belts around the planet, zones of charged particles so energetic that they would be dangerous to any unshielded spacecraft passing through. And yet from here, from this distance, Jupiter is just a bright, steady point of light in the night sky, calm and quiet, giving no hint of the violence wrapped around it. Jupiter's influence extends even beyond its magnetic field. Its gravity reaches outward along its orbit, and at two special points, one ahead of the planet and one behind. There are stable gravitational regions where objects can gather and remain. These are called Lagrange points, and at Jupiter's, thousands of asteroids have collected over billions of years. They are called the Trojan asteroids. They share Jupiter's orbit, moving at the same pace, keeping the same distance, like travelers walking the same road, never quite catching up, never falling behind. Some have been there since the early days of the solar system, drifting in quiet procession around the sun, held in place by a balance of forces so precise it has lasted longer than any mountain, any ocean, any continent on Earth. And they are still there now, tonight, circling in the dark. Just as you are resting here, held gently by your own planet's gravity, on a world with a spinning iron core, wrapped in a magnetic field you cannot see or feel, breathing an atmosphere that has been kept safe for billions of years by forces deep below the ground. The solar system is full of these quiet protections, these unseen balances. They do not ask to be noticed. They simply hold, and the night continues, and the planets continue their slow, shared turning. And somewhere, in a museum or a laboratory, a small gray stone sits under glass, a chondrite, perhaps carrying grains of dust older than the sun, older than this entire system of worlds. It does not look like much, but it remembers everything. And you do not need to remember anything right now. You only need to rest, to let the night carry you, the way the disk once carried dust, slowly, gently, towards something new. And somewhere else, not in a museum, but drifting in the dark between Mars and Jupiter, there is a world called Vesta. A small world, only about 500 kilometers across. Not much to look at from a distance, just another pale, battered rock among millions. But when the Dawn spacecraft arrived and studied it closely, it found something unexpected. Vesta has layers, a dense iron core, a rocky mantle, a thin crust, like a planet in miniature, as though it had tried, long ago, to become something larger, but never quite got the chance. Jupiter's gravity saw to that, stirring the asteroid belt, keeping the pieces apart, so Vesta remains a small body with the heart of a world, quietly orbiting, carrying the memory of what it almost became. And farther out, much farther, in the cold reaches beyond Neptune, there are other travelers, older, perhaps, than Vesta, older than most things in the solar system. Comets. They are sometimes described as dirty snowballs, and that is not far from the truth. They are loose, fragile bodies made of ice and dust and rocky debris, leftovers from the outer solar nebula, material that never became part of a planet, never settled into an orbit close to the sun. Instead, it drifted outward and froze and waited. For billions of years, a comet may drift in perfect stillness. A dark, cold body, no larger than a small town, invisible against the black. But sometimes, something disturbs it. A passing star, a faint gravitational tug, and the comet begins to fall inward, slowly at first, then faster, drawn toward the sun it has never seen. And as it draws closer, something beautiful happens. The ice begins to sublimate, turning directly from solid to gas without ever becoming liquid. And this gas lifts fine dust from the surface, forming a soft, glowing cloud around the comet called a coma, a halo of light, born from ancient ice. And then the solar wind and the pressure of sunlight itself push this material outward, stretching it into a long, luminous tail, always pointing away from the sun, no matter which direction the comet is traveling, a tail that can extend for millions of kilometers, pale and silent, visible, sometimes even from Earth, with the naked eye. It is a quiet spectacle, one that has been watched by every civilization that ever looked up. And in 1999, a spacecraft called Stardust was sent to meet one of these travelers. It flew through the coma of a comet and caught tiny particles in a special collector made of a material lighter than air. Then it sealed those particles in a capsule and sent them home. The capsule landed in the Utah desert in 2006, carrying actual grains of cometary dust, material from the very edge of the solar system's birth, brought gently back to Earth for study. And what scientists found in those grains, and in meteorites that have fallen to Earth over the centuries, was something quietly remarkable. Amino acids, the building blocks of proteins, The molecules from which life assembles itself, found not only on Earth, but embedded in rock and ice that formed before our planet existed, drifting through space, carried by comets and meteorites, scattered across the solar system like seeds in a wide, dark field. This does not mean that life came from space, not exactly, but it means the ingredients were already there, woven into the fabric of the solar system from the very beginning, part of the original recipe. And all of this, the comets, the asteroids, the planets, the moons, the rings, the dust, all of it came together in what is, by cosmic standards, a surprisingly short time, roughly 100 million years, from the first collapse of that cold, dark cloud to a stable system of worlds orbiting a steady yellow star. 100 million years sounds like a long time, and it is, longer than any human mind can truly hold. But the universe was already more than 9 billion years old when it happened. So in that context, the solar system assembled itself rather quickly, like a thought forming in a very old mind. And now it has been here for 4.5 billion years, and it will be here for a long while yet. The sun still has fuel. It will continue to burn hydrogen in its core for another 5 billion years, steadily, faithfully, warming the planets, lighting the dust, holding everything in its gentle pull. But one day, in the very distant future, the hydrogen will begin to run low, and the sun will change. It will swell slowly, growing larger and redder, becoming what astronomers call a red giant. Its outer layers will expand past the orbit of Mercury, past Venus, perhaps reaching as far as Earth. The inner planets will be engulfed or scorched beyond recognition. The oceans will boil away, the atmosphere will be stripped, and the world we know will be unrecognizable. But this is not something to fear tonight. It is simply the way stars live and age and change, the way all things do. And after the red giant phase, the sun will shed its outer layers, gently, releasing them into space as a great, glowing shell of gas called a planetary nebula, one of the most beautiful things in the universe, a soft, luminous cloud, lit from within by the tiny, dense remnant at its center, a white dwarf, no larger than the Earth, but carrying much of the sun's original mass, glowing faintly with leftover heat, cooling slowly over billions and billions of years. And the material that was released, the gas, the dust, the atoms that were once part of the sun and its planets, will drift outward and mix with the interstellar medium, and perhaps, one day, become part of a new molecular cloud, a new collapse, a new disk, a new star, with new worlds forming around it. It has happened before. It will happen again. This is not the first solar system to form from the ashes of older stars, and it will not be the last. And that thought can rest with you now, quietly, like a stone settling into still water, out beyond Neptune, in the cold, dim reaches of the Kuiper Belt. There are small worlds that most people never think about, worlds with names that sound like whispers. Haumea, a dwarf planet shaped not like a sphere, but like an elongated egg, stretched by its own rapid rotation, spinning so fast that it has pulled itself into an oblong shape, turning end over end in the dark, with 2 small moons circling close beside it. And Make, another dwarf planet, pale and cold, with an atmosphere so thin it barely exists. A wisp of gas that freezes and collapses as Make drifts farther from the sun in its orbit and then sublimates again, faintly as it draws closer. An atmosphere that breathes in cycles lasting centuries. And Eris, the most massive of the known dwarf planets, slightly more massive than Pluto, though slightly smaller in size, dense and quiet, orbiting so far from the sun that it takes over 500 years to complete a single trip around, a world in permanent twilight, where the sun is just another bright star among many. These are the outer sentinels, the farthest named worlds we know, drifting at the edge of the sun's influence, where light is thin and gravity is gentle, and time moves in rhythms too slow for us to feel. And you do not need to follow them tonight. You do not need to travel that far. You are here, resting, breathing, and that is enough. Let the outer worlds keep their long, slow orbits. Let the comets drift in silence. Let the dust carry its ancient cargo through the dark. You are already where you need to be. But even in that stillness, the outer solar system holds a memory of motion, a time when the planets did not sit where they sit now, when the architecture of this place was still being rearranged by gravity and time and the slow pull of worlds upon one another. There is a model, a quiet reconstruction of the past, called the Nice model, named after the city in France where it was first proposed. It suggests that long ago, Neptune drifted outward from where it formed, slowly, gradually, pushed by gravitational exchanges with the other giant planets. And as Neptune moved, it swept through the ancient Kuiper Belt like a hand drawn slowly through still water. Objects that had orbited peacefully for millions of years were scattered. Some were flung outward into even more distant orbits. Some were sent tumbling inward toward the sun, becoming comets, bright and brief, carrying ice from the outermost reaches of the solar system into the warm inner worlds. And some of those scattered objects settled into new orbits, locked into step with Neptune itself. Pluto is one of them. It orbits the sun 3 times for every 2 orbits Neptune completes. A quiet rhythm, a gravitational resonance, like 2 notes that always resolve into the same chord. Pluto never collides with Neptune, even though their orbits cross, because this resonance keeps them apart, always, gently, predictably. There are many objects caught in similar resonances. Their orbits reveal the sculpting that took place, the way Neptune's migration carved patterns into the outer solar system, the way gravity shaped the darkness, not with force, but with patience. And the rearranging was not limited to the outer worlds. There is another idea, called the Grand Tack. It suggests that Jupiter, the largest of all the planets, once drifted inward toward the sun, moving through the young solar system, sweeping up material, scattering asteroids, reshaping the region where Mars was trying to form. And then, pulled by the gravity of Saturn, Jupiter reversed course and migrated back outward again, like a ship that turns in a harbor and sails back to open sea. This journey, this tack, may explain why Mars is so small. Much of the material that might have built a larger world was swept away before Mars could gather it, and the asteroid belt, that sparse, scattered ring between Mars and Jupiter, may owe its broken structure to Jupiter's passage through it long ago, before the planets settled into the orbits we know today. These are not certainties. They're careful ideas, built from mathematics and observation, and they may be revised as we learn more, but they speak to something true about this place. The solar system was not assembled and left alone. It shifted, it adjusted, it found its balance slowly, over hundreds of millions of years. And there may still be things out there we have not found. In the far reaches of the solar system, beyond the Kuiper Belt, a handful of distant objects follow unusual orbits. Their paths are strangely aligned, clustered in a way that is difficult to explain by chance alone. Some scientists have suggested that a large, unseen planet, sometimes called Planet 9, may be out there, gently herding these objects with its gravity. If it exists, it would be far from the sun, perhaps 10 or 20 times farther than Neptune, a cold and solitary world, too faint to see with current telescopes, too distant to reflect more than the faintest glimmer of sunlight. But no one has observed it directly. No telescope has captured its light. Its existence remains an open question, a possibility held gently in the hand, not grasped, not dismissed, simply waiting for more evidence, or for the slow turning of discovery to reveal what is there or what is not. You do not need to solve that question tonight. Let it rest. As you rest, let the unknown remain soft and unthreatening, a door left open in a quiet house. And now, let us turn from the edges back toward the center, toward the sun itself, and the cloud from which everything came. When scientists study the sun's atmosphere, they find a particular mixture of elements, hydrogen and helium, with traces of oxygen, carbon, iron, and dozens of others. And when they study the solar nebula's original composition, preserved in the most ancient meteorites, they find nearly the same mixture, the same recipe, because the sun and the nebula were born from the same cloud, the same cold, dark gathering of gas and dust, 4.6 billion years ago. Within those meteorites, there are subtler clues, the isotopic ratios of oxygen, tiny variations in the weight of oxygen atoms differ from one meteorite to another. These differences tell scientists where in the early disk a particular grain of dust formed, whether it condensed close to the young sun or farther out, in the cooler reaches of the nebula. Each grain carries a quiet signature of its origin, like a postmark on a letter sent long ago. And the disk itself was not uniform. There were boundaries, invisible lines drawn by temperature. The frost line, where water could freeze into solid ice, sat at one distance from the sun, and farther out still. There was another boundary, where carbon dioxide could freeze, creating a different compositional zone. Each region of the disk had its own character, its own chemistry, shaped by nothing more than distance from the warmth at the center. These zones gave rise to different kinds of worlds: rocky planets close to the sun, icy bodies farther out, and everything in between, arranged not randomly, but according to the quiet logic of heat and cold. In the 18th century, two astronomers, Titius and Bode, noticed something curious. The distances of the planets from the sun seemed to follow a rough pattern. Each planet sat at a distance that could be approximated by a simple mathematical rule: Mercury, Venus, Earth, Mars, and outward, each one falling close to where the pattern predicted. It is not a perfect law. It is more of a tendency, a whisper of regularity in the spacing of worlds. And it breaks down for Neptune, whose orbit does not fit the pattern well at all. So it remains a curiosity, an observation without a firm explanation, a hint that there may be some deeper principle at work, or perhaps just a coincidence, beautiful and unexplained. The solar system is about 4.6 billion years old, roughly one-third the age of the universe itself. In all that time, light has been traveling outward from the sun, reaching Earth in about 8 minutes, reaching Neptune in just over 4 hours, a journey that seems long to us, but is only a small crossing in the vastness of this place. The farthest confirmed object in the solar system, a small, distant body nicknamed Farfarout, orbits at about 132 astronomical units from the sun, 132 times the distance between the Earth and the sun. Out there, sunlight is faint, a dim point in an enormous sky, and yet it still arrives, still touches that distant surface, however softly. Even at the edges, the sun reaches out, and you are held by that same star tonight, warmed by the same light that has traveled 8 quiet minutes to find you. You are part of this system, this ancient arrangement of dust and gravity and time. Let that thought settle, like dust in a still room. You are here, and you are resting, and the solar system turns slowly around you, as it has for billions of years, and will for billions more. To feel how vast this all is, it sometimes helps to shrink it down. If the sun were the size of a basketball, just a simple ball you could hold in your hands, then Earth would be a small bead, a tiny grain, sitting about 26 meters away. The width of a quiet street, that is the distance between us and our star, when the star is no bigger than something you could carry. Mars would be a little farther, Jupiter a bit farther still, and Neptune would be a speck, hundreds of meters out, barely visible. But the nearest star, the closest sun beyond our own, on that same scale, would be roughly 6,000 kilometers away, 6,000 kilometers from a basketball. That is the emptiness between us and our nearest neighbor. Even when you make the sun small enough to hold, the space between stars remains almost incomprehensible. It is a silence so wide, so deep, that light itself takes years to cross it. And into that silence, we sensed something. In 1977, two small spacecraft were launched from Earth, Voyager 1 and Voyager 2. They were built to visit the outer planets, to photograph Jupiter's storms and Saturn's rings and the pale blue curve of Neptune. And they did all of that beautifully. But they carried something else, something not meant for any planet. Attached to each spacecraft is a golden record, a phonograph disc, plated in gold, etched with sounds and images from Earth. There are greetings spoken in 55 languages. There is music, Beethoven, Blind Willie Johnson, a Navajo night chant, the sound of a mother's first words to her newborn child. There are images of rivers and forests and human hands, diagrams showing where our sun sits among the nearby stars. All of it pressed into a disc of gold and sent outward into the dark. Not because anyone is certain to find it, but because it felt right to try, to say, we were here, we noticed the universe, and we wanted someone to know. The Voyager spacecraft are still traveling, still drifting outward, long past the edge of the heliosphere into interstellar space. They send back only the faintest whisper of data now, and one day, they will go quiet altogether. Their instruments will shut down. Their transmitters will fall silent, but the golden records will endure, because in the vacuum between stars, there is almost nothing to wear them away. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a small star in the constellation Camelopardalis. It will not stop there. It will not orbit. It will simply drift past, carrying its golden record, its cargo of whale song and wind and Bach through the dark. No one will be awake on Earth to notice that moment. Perhaps no one anywhere will notice, but the record will still be there, turning slowly in the silence, a small golden circle, holding the sound of rain. And the solar system itself, the place where all of this began, is not standing still either. The sun and all its planets drift through the galaxy, moving together like a family walking through a vast and changing landscape. Over millions of years, the solar system passes through different regions of interstellar space, sometimes through thin clouds of gas, sometimes through emptier stretches, sometimes closer to other stars, sometimes farther away. The sky above Earth has not always held the same constellations. The stars we see tonight are a temporary arrangement, a pattern that will slowly shift and dissolve and reform into shapes no human has ever named. The galaxy is alive with motion, and we move through it quietly, without feeling a thing. And all of it, every part of this long story, the sun, the planets, the moons and comets and golden records, all of it is made from the same thing: dust. The dust of older stars. Every atom in the Earth was forged inside a star that lived and died before the sun was born. The iron in the core of this planet, the silicon in its rocks, the oxygen in its water, all of it was made in the furnace of a star that no longer exists, a star that burned for millions or billions of years, and then collapsed or exploded, scattering its elements into the dark. And those elements drifted for a very long time until gravity gathered them again into a new cloud, a new disk, a new sun, and new worlds. The calcium in the stone beneath your house was made inside a dying star. The carbon in every living thing you have ever touched was assembled in the heart of a giant long before this place existed. And you, lying here tonight, breathing slowly, you are made of the same material, the iron in your blood, the oxygen filling your lungs right now, the phosphorus in your bones, all of it, stellar ash, gathered by gravity, shaped by time, into something that can rest and breathe and wonder where it came from. You are not separate from this story. You are the story, told in bone and breath. And tonight, you do not need to hold any of it. You do not need to remember the numbers, the distances, the names. Let them go, like dust settling in a still room. The solar system turns. The galaxy drifts. The stars burn on, quietly, as they always have. And you are here, warm and still, and made of light that traveled a very long way to become you. Let your breathing slow. Let the weight of the day leave your body. There is nothing you need to do now. Nothing at all. Just rest. The stars will keep